Let's start just by looking at what is a set and how can we use it to help us organize. So looking at these sets, we often will use them to understand relationships, whether it's among living things, such as what biologists use to sort living beings into the different kingdoms. Sometimes mathematicians will organize objects into sets, looking at the different elements or the members of that set. Regardless of how you are thinking about a set, if you wanted to write it mathematically, you're going to use braces, and those are kind of the curly looking parentheses, and then you'll list out each element or each member within the braces with a comma in between. We call this the roster method of describing a set. So this example would be the set containing 1, 2, 3, 4, and 5. If we want to designate whether an element is included in the set, we use this little symbol that sort of looks like an E, but it's kind of a horseshoe with a little line through it. If something is in fact an element of that set, like 4, we would say 4 is an element of the set 1, 2, 3, 4, 5. An example of something not being an element of the set, like 7, you would say 7, and then that element symbol with a slash to indicate that 7 is not an element of that set. Now, sets are general objects. They can contain elements other than numbers. You can use the lowercase letters of the alphabet. You could write out different colors of the rainbow. You could list out whatever you wanted in a set. It does not have to be mathematical. Another thing to note with sets is that we often will describe them with a capital letter. And so the capital letter A is representing the set of all of the lowercase letters in the English alphabet. So we could say that W is an element and list out that whole long set, but it would probably be easier for us to use the letter A, the name of that set. We can call the sets whatever we want, but we typically will use them with a capital letter. Now in mathematics, we have different sets of numbers that we often refer to, particularly when you're studying algebra. So we have what's called the natural numbers. Those are going to be the numbers that we encounter most of the time in this class. These are those counting numbers. Basically, if you can count it on your hands and toes, then it would be a natural number. Now, of course, you can keep counting as long as you possibly can, but the natural numbers are those counting numbers, 1, 2, 3, 4. Whole numbers get just one additional number. We also include 0. So the natural numbers start at 1, the whole numbers will start at 0, but it will include those same numbers. Integers, that's where we take the whole numbers, but then we add all the negative numbers. And then finally, rational numbers. These are all of our fractions, all of our repeating decimals, all of the numbers that can be expressed as a fraction. But not all numbers can be expressed as a fraction. Sometimes you have things like pi that you studied in geometry. And those would be for those decimals that just keep going on and on and on. Those are considered irrational numbers. And then finally, your real numbers, that's the set of all of the numbers that you encounter. Now, there are imaginary numbers, but we will not be talking about that at all in this class. So real numbers will cover everything that we might encounter in this course. Sometimes it gets really burdensome to write out all of the elements of a set. So anytime that you see 3 dots, we call those the periods of ellipsis, and that's just helping us see that the pattern is going to continue in the manner suggested by the elements that are listed. So we don't need to write out every single negative integer in order to help someone see that we're talking about the negative integers. We would just do the dots and the -4, -3, -2, -1. We could never actually write them all out anyway because we would keep having to write them. If we wanted to show that the positive integers were continuing on, we could do 1, 2, 3, 4, and then ... telling us that you're just going to keep going in the same pattern. Earlier, I spoke about rational numbers. These rational numbers are basically any number that can be written as a fraction. it's probably easier for you to think about the decimals. And anytime you have a decimal that terminates or stops, or a decimal that repeats, like you see 3 over 11 is 0.27 repeating, those would both be considered rational numbers. Irrational numbers would be decimals that don't end or don't have a repeating pattern. And so one of the very popular values that we have in that irrational set would be pi. It shows up a lot in geometry. The last thing that we want to talk about, just with some of the number theory, this is not a huge part of this class, but it's important for us to discuss this so that we have something that we can practice applying our ideas of set theory. We need to talk about prime numbers and composite numbers. So you might remember that a prime number is any number greater than 1 that's only divisible by itself and 1. So for example, 7 is a prime number because you cannot divide 7 by any other number other than itself and 1 and get a whole number. Composite numbers, on the other hand, are numbers that you can divide by something other than 1 and itself. So something like 12 would be composite because you can divide it by all sorts of numbers, 2, 3, 4, and 6. Now that we've done a brief review of some of the number sets that we have in mathematics, now we can look at how we apply the ideas of sets. So if we wanted to write the set of prime numbers less than 20, what are all of the numbers that are not divisible by anything other than 1 and themselves? Well, it has to be greater than 1, so we're going to start at 2. 2 can only be divisible by itself and 1. 3 also can only be divided by 3 and itself. We'll skip over 4 because 4 is divisible by 2, so 4 would not be prime. The next one would be 5, and we can keep going through the list. The rest of them are 7, 11, 13, 17, and 19. The numbers that we skipped all could be divided by some other number. For part B, if we wanted to write the set of negative integers greater than or equal to -8. So this one, we would not have to use the periods of ellipsis because there's really not that very many numbers in this set. -8, -7, -6, -5, -4, -3, -2, and -1 would give you all of the negative integers greater than or equal to -8. Notice here that we did include -8. Now for C, we want the even whole numbers less than 10. Well, whole numbers start with 0, and we will consider 0 to be even for the purposes of this class. So we have 0, 2, 4, 6, and 8. We will not include 10 because 10 is not less than 10. Every once in a while, we will end up with two sets that are equal. We consider two sets to be equal if they have exactly the same elements. There's nothing different about the two sets. Another thing that we encounter from time to time is what's called the empty set. And that's a set where nothing holds true. So you might think of this as the set of even and odd numbers, or any numbers that are both even and odd. That's a better way of saying that. No number is both even and odd. You're either even or you're odd. So if we wanted to try to create the set of numbers that are both even and odd, we couldn't come up with anything. And so that would be the empty set. The empty set, you can write that as a circle with a slash through it, but you would not write brackets around that. That would imply that the set actually contains the empty set, which is a little confusing. So anytime you have the empty set, just draw a circle with a slash through it.